that something's compounding every 4 years. That means within every year it's compounding 1/4. All right. So what you're looking at is there's no real clean way of doing this except the fact of 4 years. So think of it this way: when do the Summer Olympics occur? Don't say the summer. Every 4 years, right? How many Olympics occur in 20 years? 5 of them. Okay. That's the idea. So this, in 20 years span, because they're talking about from this year to the year 2000 to 2020, it happens how many years? 20 years. So if it's going to compound once every 4 of those, how many times did it compound? 5. From 20,000 or from 2000 to 2001, how many years is that? 1. So it would compound 1/4. Okay, that's where that comes into play. And then the C is this year. So for C problem A. Oh yeah, you got some really big number. And then for D, it was 100 years because it would be 2100, right? Yeah. And then that was, so my numbers that I got here, because with the rounding part, I have 12,394 for part A, 11,406, and then what'd you get for C? I forgot. I forgot what year we used. I didn't write that down. What'd you get for C?
I just don't.
Okay. No big deal. What'd you get for C?
Basically, I was confused by the 1/4 thing. So if it's every 4 years and it's 2001, it only goes up by 1 year. So wouldn't you divide 2.1 divided by 2.1 divided by 4 now? What would you?
How many years is between 2000 and 2001? What's 1 divided by 4? Don't think that. Oh, yes.
And that would be
Your exponent. Yes, sir. Bless you.
Could you use the compound interest formula, except instead of putting a whole number for the number of times per year that it goes up? Could you put
The fraction amount?
Yeah, 0.25?
It should work, but when you don't use that compound one because that's for when you're dealing with money. Remember, like I was saying, 97% of the time it's money.
What if you wrong on the part B?
right.
Very possible that I might have bumped the wrong number. So,
For part B? 11,200.
okay. It's very well that I typed the wrong button. I hit the wrong button. I might have accidentally hit. I wonder what I did for the rate. I remember if I typed my rate incorrectly. Maybe I missed the decimal.
What did you get for part B?
18,782. Yeah, guys, I might have bumped the wrong number on my part B there. I apologize. It could have been something silly. No big deal.
Wait, you got 18,782.
Yeah, I didn't get that either. I got 16,920.
I must have definitely hit the wrong button on mine.
Is that what you got?
Oh no, I was using a weird compound interest.
So I bet you anything after I did that one, because I was at basketball, got up and restarted the calculator. I wonder if I retyped in the 11,171 as maybe 11,711 or something like that. It's probably something stupid like that. But the general idea is fine. You just take the number of years divided by 4, and that's what your exponent becomes. Okay. I probably just bumped the wrong button. I have it written, but I didn't write down what I typed there. No.
But isn't there parts where you're calculating?
Correct. There's a calculator and I calculator. We'll talk about it. Hi. You're getting annoying today. You think you want to know stuff. Welcome back. It's not money. Those are for money.
The compound interest.
That's a compounding interest money problem. This is just a number of time the interest change, the percentage growth or decay changes. And that's just all this is.
So instead of that, we put the extra.
Yeah, like I said, the two answers that I just got here, my best guess was I bumped the wrong button as I was reading it. I wonder if I did it like I'm saying 11,711, 7171. I bet you to be off by that little bit of amount from what you guys were all getting, it means I just transposed a digit. So, and obviously when it gets to quizzes and stuff, I'll start to recognize. I'll see everybody's getting all the same number, and then all of a sudden I don't have this, and I'll be like, oh, I wonder if I hit the wrong button. And I scroll all the way back up to my calculator to see what I had pressed, and Lord knows you'll find that you hit a 2 instead of a 6. So it happens. So no big deal. 6 was a decay problem. Again, same idea. It was changing every 3 years by that percentage. So I would take the number of years elapsed divided by 3. So the first part on 6, you started with 4,324,000. It's decaying at 11%. This was the literacy rates, I believe. I'd read the whole problem, but I forgot it.
When does it start?
This year. To use this year. Okay. It's convenient that this year works out to be multiples of 3, so you go up to the rest of these answers. So in the year, so this year an estimated 4.3 some odd million people are illiterate. Blah, 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 blah. It decreases by 11% after every 3 years. So from 2020 to 2035, how many years elapse? So your x1 becomes 15 divided by 3, which gives you 5. Okay. If I did that, I got that's 2,414,547. I do that again with between 2020 and 2095. It becomes 75 over 3, so it's 25. I got 234,766. And then the last one was a third of 135 years, and I got 22,826. Are you doing decimal, people?
Yeah.
Are you putting dollar signs in front of them too? You did, didn't you? Yep, I figured.
What people are money too.
You're not the only person that does that. You were thinking about the person on the $30 bill.
People are worth money.
Time to end our conversations from this year. I pay attention. Shut up. 9, let's see. Again, this is like every 6 years. So the time elapsed, the first one was 12 years. How many times does it happen? It happens twice. So it's 12 divided by 6, you get 2. So my first part was approximately 541,500. After that, it was 60 years elapsed. Every 6 years means my x1 becomes 10. And I have approximately 359,242. And then lastly, it was 21 over 6, which becomes a crummy fraction, which is fine. You can leave it like that. The calculator would do it. And I got 500 and, did I say 300? I said 3. No, whatever. And then this one was 501,399.
Okay, next time when you do this, for people that like care, like, can you like split B and C so
I know, that's what I was thinking. Like, wait, did I flip that? And then I remembered, oh, that's right, because the one was 4 years than the other.
Yeah, because it gets
When I want to put
all the way down to 2010.
the last couple were also pretty easy. There was one part on 3 that I forgot to tell you guys. Don't worry about effective annual interest rate. I'm not going to worry about asking you guys what the effective annual interest rate winds up being. That's something you learn a little differently in like when you take an econ class. It's not a big deal. Here I was just looking at how much for every dollar. I wanted to see if you guys figured out how to set that up. When they're talking about for every dollar you owe for a year, what's your initial amount you're looking at? $1. So you're looking at $1. So when you think about it, you're $1. And then you have, this is the compounding annual interest for monthly, so we'll do that one first. So it's 0.129 over 12. It's 12 to the 1. Now I got this one to equal 1.1369. Now I'm bringing it out to a couple extra decimals.
I swear to God, bro. Oh, man. You need to be my head on your left.
Just talking to himself.
Quite possible. One of his friends.
You just straight up.
Okay. People, I was just having a bad day. Now, when you think about this one here, this is, let's see, this is what's inside the parentheses now. We want to break it down. This is your, oops. See what I'm doing there?
We didn't do the.
Huh?
Wait, we didn't do the read on this page.
We did.
Well, I didn't.
Well, that's okay. The reason why I wrote this out to 4 decimals is because if you round this here, you get 1.14. And I wanted you guys to remember that in the parentheses, your percentage here, your rate would be 13.69%. Does that make sense? I just wanted to see how you were setting this one up, because now in part B, when you do that, you've got your 1 plus 0.129, 365, 365, 1, and there's a 1 here. Here, I got approximately 1.13766. So that means my percentage rate is 13.77. This one was 13.69. So that's where the slight variance becomes, because if you round this out to 2 decimal places, you get the same thing. I just want to see if you know how to set that through up. So the idea here is for every dollar you don't pay off, you're looking at you owe 13.69 cents. 13.7 something cents. Yes, sir.
Wait, how did you? Oh, I made that on the second.
It's a great conversation.
Why is it always one?
This formula. The formula.
But if you were to solve that,
What do you mean?
if you were to solve.
Yeah, you got this one. Yeah. What I was doing here is that because this is a growth problem,
Yeah.
this 1 plus R is the R is the percentage. So I was just showing you how you get the percentage there. Okay. All right.
What's the name of the annual rate?
That's something we don't talk about in this class. That's something I do in econ. So I'm not going to ask anything like that. I just wanted to show you guys how this sets up. That's all.
What do you got?
It's an economics thing. Don't worry about it. How to calculate that. It's a different setup. Yes, ma'am. If it says it's compounding monthly, compounding daily, compounding something like that. If it says that it's compounding monthly, semi-annually, daily, bless you, anything but annually, it's that one. If it's compounding annually, it's still over 1. It doesn't change. All right. And then the last one's number 5. It was just compounding. It was an exponent. Plus, it was a compound continuously. So it was an E value. So I got 141907 and 201375. And then the last one was the decay at 12% for 5 years, and I got 13193 and 30 cents.
For number 5, what is the 1,000? Is that the answer? Is that the initial?
1,000?
Yeah.
It's initial.
Okay.
Wait.
It's compounding continuously, so the principal amount is the 1,000. E to the 0.35 times the time in years.
I used the wrong.
Okay.
So the other thing I wanted to talk about is how poorly you guys work with fractions. The idea of how the graph stuff that we were looking at yesterday, barely a third of you guys knew how to work with your fractions. That's embarrassing. I hate to say it like that, but it's kind of embarrassing. The other part of it was the fact that when we set things up the same way, yes sir.
What was grade 12?
I don't know, I haven't decided yet. Probably not.
Oh, you're not getting it back.
So what happens here is that you guys need to understand how you work with fractions, how you work with fractional exponents, how you work with negative exponents, things like that. We just got done with a chapter on exponents. We just got done working with negative exponents. We just got done distributing and solving and flipping fractions that have negative exponents. We just got done doing all of that. So that's why this first part of just straight graphs should have been a lot easier than what it was. Whether it was combination of just dumb mistakes or complete, total, utter, like not finishing things. But what I want to do is kind of look at, I'm going to look at the 4-2 or 8-2 one here. What number was it? It was, I'm going to do number 11, but I'm going to change it just ever so slightly. I'm just going to throw an H in there. Ladies and gentlemen, every time we do a growth or a decay problem, we do it the exact same way every time. Every time we do this, we're going to label out all of our parts. We're going to use the same sets of ordered pairs to get our parent function, and then we shift them from there. Whenever you have exponential growth, exponential decay problems, you are always, always, always using 5 values of x. -2, -1, 0, 1, and 2. That never changes. Those are the only ordered pairs you're supposed to use. Okay? Not just picking up a whole bunch of them, substituting them into the whole shifted function and going for it. That is not how we do this. Everything is parent and shift. Okay? So, first things first, you label out. A is 2, B is 1/3, H is 2, and K is -4. Since I know that it's going to be a decay problem because my B value is between 0 and 1. Okay. My A value is positive, so that means that my decay is going to go from the top down. All right. The H tells me that it's going to move to the right 2, and the K values can tell me it's going to move down 4. So I make a little note of that, so when I have my ordered pairs, I know what to shift. As I start moving it. Your parent function, -2, -1, 0, 1, 2. This is always, always, always how you start. You guys got to remember that. I've never wavered from that. Your parent function that you substitute in is your AB to the X. Always. Not just B to the X, not A to the X. It's AB to the X. And then you have to remember how to use fractions. When you substitute in the -2, write it out. 2, 1/3, -2. That means the fraction is being raised to the -2. Any fraction that's raised to a negative value means what do you do to the fraction? Flip it. What's 1/3 squared? I'm sorry, 3 squared, excuse me. 9. What's 9 times 2? What's 1/3 to the -1? 3. What's anything to the 0? 1/3 to the 1? 1/3. So you get 2/3. And then lastly, you get 1/9, so it becomes 2/9. That's how that works. It's that fast. Don't overthink yourselves. Okay? Yes, sir.
I was just going to say, can I take a picture of this? I didn't want to forget everything.
So use parent functions. Yes, use parent functions. Okay? Your second set here, you just write down what your shift was. What was it, +2? You should not have to math anything from there. You're just going from your ordered pairs. What's -2 plus 2? But are you resubstituting in anything? No. -2 and -1 and 2. 1, 2, 3, 4. Okay? Go through the rest of them. 18 minus 4. 6 minus 4. 2 minus 4. 2/3 minus 4. -3 and 1/3. What's that? Mixed numbers are like I said, there's a time and a place for mixed numbers. I hate them, but this works the best here. Okay? They work so well here for this kind of stuff. And then -4 back out, and you add the 2 ninths, you wind up with -3 and 7 ninths. Remember all the times we talk about how much more do you need to get to a hole? Well, 2/3 is 1/3 away from the hole, so you just move it out. 2 ninths is 7 ninths away from the hole, so just move it out. Okay? Those are my ordered pairs. From here, we have to graph and do our asymptotes and stuff. Okay? Plot your parent function. Your parent function always has a horizontal asymptote where? 0. Good. So we have our 0 asymptote. From here, I'd go through my ordered pairs. -2 and 18. -2, 18, it's up here. Okay? -1 and 6. 0 and 2. 1 and 2/3. And 2 and the ninths. And this one is a dotted line as it comes up. Okay? Sir? Parent functions are always dotted. They are there just to give you guidance to what your shift would be. Kind of like a parent. Relabel. 0 and 14. Up here-ish. I don't know. 1 and 2. 2 and -2. 3 and the third here, then we're moving down to. Nope, I didn't go farther. Sorry, I did that last hour too. These 2 points gotta move down. Here. And this one's solid. Is it okay that your shifted function crosses over? Yes. Yes. Perfectly fine. That has no issues. So now, your asymptote is at y equals -4 for your asymptote. And this is always your shifted one. Bless you. Your domain. All real numbers. Exponential growth, exponential k, domain is all real. Your range, bless you. Is the graph above or below your asymptote? Above. Yes, sir.
We're supposed to write that stuff on the
I
scale too.
said that. Don't forget domains and ranges and all that too. Okay. Your range
Wait, there's nothing.
is y values that are greater than -4. Bless you. If it was below, if the graph was below, that's why it's so visual. If it was below, then you would say y values that are less than. Right? That's how this stuff works. This doesn't change, guys. The mathing of this is very simple. So if you got graphs that were linear and moving back and forth, or parallel lines, or this stuff, bless you, or lines that look anything like that, because you were just picking out pairs because you freaked out about fractional things. Freak out about it. Okay? Let's look at another one. Let's look at a growth. Let's look at a growth one. On 8-1. I'm going to look at, what did I do before? I'm going to look at 18, but I'm going to change it. I'm going to put a -1 in front of it. I'm looking at 18, but I'm just changing it ever so slightly, just so you guys can see what happens if you've got an A value that's negative. All right? So, 10-10, oh, here we go. So remember, when you're doing this one here, same thing, label A, B, H, and K. Our A value, -1, B value, 2, H, +1, K, -3. So it's x plus 1, y minus 3. That's how they set up. Okay? Parent function, always AB to the x. Negative 1 times 2 to the x. 2 to the negative 2. Well, that just means it's 1/4. And then you multiply it, you get your negative 1/4. Good. Now you get negative 1/2, negative 1, negative 2, and negative 4. See how fast that is? That's why we picked those numbers, because they're easy to work with. Shift it. Plus 1 minus 3. So, negative 1, 0, 1, 2, 3. Negative 3 1/4. Negative 1, 3 1/2. Negative 4. Negative 5. Negative 6. I'm sorry, negative 7. Sorry. It's kind of like-ish 18. I just put an A value out in front of it. Okay? And then from there we plot. Yes, ma'am.
So you're shifting negative 2.
Yeah. Negative 1. Yep. Order of operations, guys. A lot of you are forgetting about order of operations with this too. You're forgetting a lot of order operations.
So that's the negative 1. So that's there's negative 1, and you would have sit also
No, because it's before it. This is the negative 1 being raised to that power. Yep.
But is it?
2 is, yes. So what's 2 to the negative 1? Think order of operations. When you have order of operations, you have negative 1 times 2 to the negative 1. It does do what first? Parentheses, exponents. So this becomes negative 1 times 1/2. Gotta follow your exponent rules. Then the graph of it then is relatively quick. Wrong button. Negative 2, negative 1/4. Negative 1, negative 1/2. 0, negative 1. 1, negative 2. 2, negative 4. Negative 1. Negative 3 1/4. 1, 2, 3 1/4-ish. 3 1/2-ish. Six and 7, right? Yeah. Domain all real. Range y less than negative 3. I was just stepping back and having a sip of delicious buttered caramel coffee. Buttered caramel coffee. It's very good. Coffee. I buy flavored coffee beans and I mix it with regular beans so it just kind of it doesn't get to be so sweet. It just gives a nice little extra flavor to it. Here. Sir.
Oh, yeah.
In the roasting, they add additives and chemicals and stuff to make it die. So it's delicious. Oh, that's typical. Okay. No. After that, remembering. Correct. The B value won't because the A value is what negates it. All right. B value. The B value is going to be between 0 and 1 for decay, greater than 1 for growth. And then the A value just makes it either sloping or for decay coming down this way, growth going up this way. This one is still a growth, but it's diving as opposed to going that way. Because remember, the growth one would just kind of go do this. So they just kind of flip over each other. So the decay goes this way or it goes this way. Fun. The other part on here was the. I thought you get the one you had, so gotcha. The other part on here was when we did this, and I know this was relatively quick, but what happens if you have this? What is it? Very good. Yeah, it's 4e to the 3x. Remember, same base, different exponents. Treat it the same way. E to the 1x. Yeah, very good, very good. Now, what about 216? What's
Just
cube?
keep dividing it by 2. Until you find
Yeah, that'll work. It's 6, though. Think of it this way. If you know that the cube has to end in a 6, that means you multiply the square by something that ended in a 6. So you just go through them. What perfect square ends in a 6? You keep because you know 6 times 6 ends in a 6. 36 times 6 is 216. So this becomes 6 e to the 2x cube root e to the x. How many? 3 goes into 7. How many times? Twice, and then there's 1 left over. Okay. Sir. Just reminded if you did it. Remember how do you tell it's growth or decay depending upon the rate value when you're looking at the exponential stuff? Remember, we don't really graph these things all that much because the only point you can ever put was just 0 for x, and you just kind of do the direction. But you can always tell whether or not it's a growth or decay. Remember the R value, because for the exponential growth ones, I'm sorry, it was, what was it, A, sorry, it was E to the RX was the generic, and if R was positive, it was growth, R was negative, it was, yeah, plotting those is just kind of silly. Yes, it will be calculator, non-calculator. Obviously, the calculator part will be a whole lot of word problems. That's kind of how you need to use those. And then the non-calculator, you could probably test to wind up being, I don't know, graphing, you know. So yeah, other than that, it should be straightforward. You can do this without a calculator also. Sure. Because you just need to be the
Oh, yeah, sure. No, anything other than that? Just graphing?
I could put in, like logarithms. Yeah, because then next week we'll start 8-4. 8-4.